Welcome to Danesh Academy, your gateway to easy and fast education. In this segment of our video, we delve into the fascinating world of OTFS systems, exploring cutting-edge technology and advancements in the field. First, we will provide a brief history of the OTFS system. Next, we will present the fundamental theories and structure of OTFS in detail, along with its relationship to and differences from the OFDM system. We will also outline the benefits and applications of the OTFS system, citing examples of practical tests conducted by renowned companies. Finally, we will elaborate on the Python code for the results that have been presented. The concept of OTFS technique was initially patented in 2010 by Rani Hadani, a mathematician and professor at the University of Texas at Austin. He specializes in representation theory and harmonic analysis with the applications to signal processing. Hadani is renowned for developing orthogonal time-frequency space modulating techniques, a method used to enhance the speed of wireless 5G communication, and is being considered for implementation in 6G technology. He has been granted over 300 OTFS-related patents. In 2011, he co-founded the software-based company Cohere Technologies with Slav Rakib to further developing the concept of OTFS for practical applications. In 2017, a paper titled OTFS Modulation introduced OTFS at the IEEE International Conference on Communications. During the inaugural 6G Evolution Summit event opening keynote in December 2022, a moderator from First Wireless referred to Hadani as the father of OTFS. Fundamental concepts are listed for your reference. First, the blocks of the OFDM system will be explained, followed by an overview of the OTFS system blocks. Subsequently, the OTFS modulation and demodulation processes, which constitute the transmitter and receiver parts of the OTFS system, will be detailed. The model of the channel in the OTFS system will then be introduced. Given that OTFS systems operate in the Delay-Doppler domain and OFDM systems in the time-frequency domain, we will explore how to transition the coordination from Delay-Doppler to time and frequency domains and vice versa. Finally, the general transformation of coordinates among Delay-Doppler, time, and frequency within the framework of a fundamental triangle will be presented. In an OFDM system, there are K subcarriers and L time slots used to transmit information symbols across the channel. Consider the small rectangular section within the OFDM system represents the time domain, as the input ST and output RT of the channel are in the time coordinate. However, consider again in the larger rectangular section, as time domain signals are transformed to the frequency domain using the well-known fast Fourier transform, FFT, and inverse FFT. Here we have the time frequency domain. In the context of the OTFS system, the inverse FFT corresponds to the Heisenberg transform, while the FFT corresponds to the Wigner transform. The input and output of the OFDM system are in the frequency coordinate, because the coordination of the OFDM system operates in the frequency domain. The main distinction between OTFS and OFDM is the inclusion of one additional block, which is the inverse symplectic finite Fourier transform ISFFT. This two-dimensional precoder processes signals in the Delay-Doppler domain. As observed, an ISFFT block precedes a Heisenberg block, while an SFFT block follows the Wigner block. In the OTFS system, XNM serves as the input and YNM as the output. The index N denotes delay or range, and the index M signifies Doppler or velocity. Delay-Doppler variables are commonly employed in radar and communication theory. In radar, they aid in representing and distinguishing moving targets based on their delay or range and Doppler or velocity characteristics. In communication, they represent channels through a combination of time and frequency shift operations. From a broader perspective, OTFS establishes a conceptual link between radar and communication. The transmitter of OTFS, depicted in the upper rectangle as the OTFS modulation section, comprises ISFFT and Heisenberg transform blocks. Conversely, The receiver, i.e., OTFS Demodulation, involves SFFT and Wigner transform blocks. The transmitter converts the signal from the delay-Doppler domain to the time domain for transmission through the channel. Conversely, the receiver transforms the signal from the time domain back to the delay-Doppler domain. The delay-Doppler representation offers a generalized view of time and frequency representations. In the next sections, we will delve into the details of the OTFS blocks. OTFS modulation is a novel two-dimensional modulation scheme. In contrast to conventional OFDM modulation, OTFS modulation adopts the delay-Doppler domain signal representation instead of the time-frequency domain, where the channel responses are relatively sparse and robust. Furthermore, OTFS modulation utilizes the two-dimensional ISFFT to convert the delay-Doppler domain signal to the time-frequency domain. Therefore, in OTFS modulation, the first block is ISFFT, establishing the mathematical relationship between x and m in the delay-Doppler domain and x sub tf of kl in the time-frequency domain. Note that there are n delay slots and m Doppler slots. The shape of the signal x of nm and the delay-Doppler coordinate is represented on the left side. It is important to note that we have considered the noise effect on the input signal in our simulation. The shorter side lobes around the main lobe or talus lobes indicate the noise effects. As you observe on the right side, the signal x of nm transforms into an output signal with a time frequency shape. This transformation is governed by the mathematical relationship we explained earlier. When the output of the ISFFT block enters the Heisenberg transform, or IFFT, the output signal of this transform is in the time domain. Please look at the shape of the signal S of t. Here P represents the number of resolvable paths, while h sub I, tau sub I, and upsilon sub I denote the channel coefficients, delay shifts, and Doppler shifts corresponding to the ith path, respectively. The representation of a linear time-varying channel in the delay-Doppler domain is given by the formula below. Instead of the time-frequency domain, the delay-Doppler domain signal representation results in relatively sparse and robust channel responses. The properties of the delay-Doppler domain channel give rise to the placement of symbols in this domain. This allows information symbols to directly interact with the delay-Doppler domain channel response, leading to a simpler input-output relationship compared to OFDM modulation, particularly in high-mobility channels. Thanks to the ISFFT, each delay-Doppler domain symbol spreads across the entire time-frequency domain, expressing the fluctuations of the time-frequency channel response throughout an OTFS frame. As a result, OTFS modulation demonstrates strong resilience to Doppler spread and has the potential to achieve full channel diversity. Consider the shapes. The signal R of t is the output of the channel for input signal S of t. As you observe, the channel characteristics in the delay-Doppler domain have an impulse shape, and there are two irresolvable paths, i.e. two impulse signals. When the output of the channel block, look at the shape of the signal R of t. The R of t enters the Wigner transform, or FFT. The output signal of this transform, x sub tf of kl, is in the time-frequency domain. Here we establish the mathematical relationship between y of nm in the delay-Doppler domain and y sub tf of kl in the time-frequency domain. This relationship is defined within the context of n delay slots and m Doppler slots. OTFS demodulation involves the utilization of the two-dimensional SFFT to convert the time-frequency domain signal into the delay-Doppler domain. Therefore, in OTFS demodulation, the final step comprises the SSFT operation. The shape of signal y of nm in the delay-Doppler coordinate is depicted on the right side. It is important to note that we have taken into account the noise effect on the input signal in our simulation, and you can observe this noise effect on the output. The shorter side that fluctuates around the two main lobes signifies the noise effects. The signal y of nm transforms into an output signal with a time frequency shape, as seen on the left side. This transformation is governed by the relationship specified by the mathematical formula we discussed earlier. Here we will explain how to transform from the delay-Doppler domain to the time-frequency domain and vice versa. For example, let's consider the OTFS modulation section, which converts the signal x of nm from the delay-Doppler domain to the time domain. This transformation can be easily achieved using a simple Z transform formula as shown at the bottom of the page. When dealing with a signal like phi of tau epsilon in the delay-Doppler domain, where tau represents the delay and epsilon represents the Doppler variable, the indices n and m correspond to the delay and Doppler variables respectively. By substituting the function of the delay-Doppler signal into this formula and integrating from 0 to a certain value of epsilon sub r, the transformation can be completed. To speak generally about transforming between the delay-Doppler domain and the time-frequency domain, you can employ the Z transform formula. This formula facilitates the transformation of these domains into each other. The fundamental principle is that to convert from the delay-Doppler domain to the time domain, you utilize the Z transform Z sub t, and to convert from the delay-Doppler domain to the frequency, you employ Z sub f. When transitioning from frequency to time, as you are aware, the Fourier transform is utilized. The relationship between the Z transformer and the Fourier transformer is expressed as Z sub t multiplied by Z sub f, resulting in the Fourier transform. There are much more benefits for OTFS systems, but we mention some of them. OTFS system achieves stable fading performance by spreading the signal energy over delay-Doppler domain. This spreading mitigates the effects of deep fades that are common in wireless communication channels and makes a full channel diversity. OTFS system is particularly well suited for high-frequency applications such as terahertz bands and beyond due to its ability to combat the challenges associated with high Doppler shifts and delay spreads in wireless communication channels leads to efficient use of available bandwidth. OTFS system is spectral efficient due to its two-dimensional processing approach, which optimally utilizes time and frequency resources and contributes to reducing packet loss and improving reliability of wireless communication systems. OTFS system achieves signal separability and allowing for separation of different signal components. This approach helps in mitigating inter-carrier interference (ICI) and inter-symbol interference (ISI). OTFS system is well suited for ultra-reliable communication in hostile and high-mobility environments. Resilience to fading and interference improved channel estimation and equalization capabilities, and its robustness to delay spread, Doppler shift, and distortion effects. OTFS modulation is a suitable waveform for integrated sensing and communication, i.e. ISAC, in radar and communication systems, because it is able to support simultaneous radar sensing and communication functions, and its robustness to interference, channel impairments, and high Doppler tolerance. In dynamic networks with wireless fast-moving scenarios, spectral efficiency is crucial to accommodate the rapid changes in channel conditions and user mobility. The system's ability to handle these challenges positions OTFS as a promising choice for applications requiring reliable and high-performance communication. OTFS modulation is a waveform modulation technique that is particularly well suited for high-speed communication systems such as hypersonic communication. The advantages of OTFS make it a compelling option for enhancing the accuracy and reliability of positioning and navigation systems in various environments. The unique characteristics of OTFS system make it a promising technology for satellite communication systems. Satellite operators can enhance the quality of service and expand the capabilities of their communication networks. The application of OTFS system in IoT and machine-to-machine communication can lead to more reliable, energy-efficient, low-latency, and secure data transmission for a wide range of IoT devices. With OTFS benefits, IoT networks can achieve improved performance, connectivity, and scalability, enabling the seamless integration of smart devices and enhancing the overall efficiency of IoT ecosystems. Online gaming requires real-time interaction between players, where low latency is essential to ensure responsive gameplay. OTFS technique can help reduce latency in mobile communication systems, enabling quick and reliable data exchange between gaming devices and servers. Reliable and low latency communication is critical for ensuring the safety and efficiency of self-driving vehicles. The application of OTFS modulation in autonomous driving can enhance the reliability, safety, and efficiency of communication networks, which achieve low latency, secure, and resilient communication, enabling seamless operation of connected and automated vehicles in complex traffic environments for self-driving vehicles. C-Spire, formerly known as Cellular South, is a regional telecommunications company based in Richland, Mississippi, United States of America. Deutsche Telekom AG is a leading telecommunications company headquartered in Bonn, Germany. Telefonica SA, commonly known as Telefonica, is a multinational telecommunications company headquartered in Madrid, Spain. These companies have most likely tested the channel characterization, performance, data analysis, optimization, interference, and reliability to evaluate the technology's suitability for telecommunication network infrastructure for practical applications. Here we explore OTFS Python code. We start with the setup of essential parameters. These parameters include the symbol duration t and the Doppler spread delta f. Additionally, we prompt the user to input values for m, n, and p, which determine the system's dimensions and the number of channel taps. Moving on to modulation, we witness the translation of symbols onto the Delay-Doppler grid. Here, we generate the transmitted signal in the Delay-Doppler domain, utilizing given symbol coordinates. This process involves employing sync functions to modulate the symbols and then converting them to the time-frequency domain through FFT and IFFT operations. The next stage involves channel effects. We introduced randomness by generating channel coefficients, delays, and Doppler shifts. The received signal is then formed by applying these effects to the transmitted signal. Additionally, we illustrate the channel matrix, which accounts for the channel characteristics. Demodulation is a crucial step in the OTFS system. Here, we first add wide Gaussian noise to the received signal to simulate real-world conditions. Subsequently, we reverse the modulation process, converting the received signal back to the time-frequency domain. This prepares the signal for further processing and decoding. Plot functions aid in visualizing the various stages of OTFS modulation and demodulation. We present three types of plots: three-dimensional bar graphs for depicting delay-Doppler domains, surf graphs for time-frequency representations, and three-dimensional line graphs for visualizing signals in the time domain. These plots provide insights into signal behavior and channel effects. Finally, we showcase the results of our OTFS system. This includes visual representations of the transmitted and received signals in both time and delay-Doppler domains. Through these plots, we gain a comprehensive understanding of signal propagation, channel effects, and the effectiveness of demodulation. And that concludes our OTFS tutorial. From the basics to Python codes, we've covered it all. Don't forget to subscribe for more tech tips and tutorials. Like and leave your comments below. Keep exploring, and I'll catch you in the next video.